In 2015, the European Union and nations around the globe committed to an ambitious, legally binding target, climate neutrality by 2050. To meet that goal, the world's passenger vehicle fleets have to transition to electric power. But that transition faces a significant economic barrier. Despite the mandate, electric vehicle sticker prices remain too high for average buyers, slowing customer adoption. The battery pack is the single most expensive component in the car. Today, the market is dominated by lithium-ion NMC chemistry, which relies on a precise mix of nickel, manganese, and cobalt. Relying on lithium involves a heavy environmental cost. The extraction process is resource-intensive, requiring massive amounts of water and leaving behind a significant physical footprint, all while being tied to geographically concentrated supply chains. We're attempting to build a clean, globally accessible transit system on top of a foundation that relies on complex, environmentally taxing raw material extraction. Sodium-ion batteries, or SIBs, offer an alternative. They use the same electrochemical principles as lithium-ion cells and can be produced on existing manufacturing lines, but they replace the lithium with sodium. Sodium is the sixth most common element in the Earth's crust. It is ubiquitous, found in abundance in seawater and in massive underground rock salt deposits that are distributed globally. This abundance allows manufacturers to bypass the supply chain bottlenecks associated with lithium. Because the raw materials are easier to source, the entire extraction process is cleaner and less expensive. Replacing the expensive, specialized minerals of a lithium cell with common sodium allows the final price of the battery and the car to drop significantly. However, swapping elements at the atomic level comes with a specific engineering trade-off. Sodium ions are physically larger and heavier than lithium ions, taking up more space per unit of energy. Because of this size difference, fewer sodium ions fit into a fixed-size battery casing, resulting in lower volumetric and gravimetric energy density. In practical terms, this means that to achieve a 400-mile range with sodium, the battery pack would be too large to fit within the physical frame of the car. A study by the Technical University of Munich mapped this spatial constraint. On this contour plot comparing lithium to sodium, the right hatched areas represent configurations where battery volume exceeds available chassis space. The x-axis shows the physical limit. Capacity cannot exceed 59 kilowatt-hours. Because of these geometric restrictions, sodium-ion batteries are not suitable for luxury, long-range cars. They are physically limited to smaller and mid-size vehicle segments. While that 59 kilowatt-hour limit prevents sodium from competing at the high end, it makes the technology ideal for the 150 to 250-mile vehicle range. This sensitivity analysis chart tracks the battery-related cost per kilometer for sodium cells. The central line shows how these costs evolve across different capacities. Even when factoring in its lower energy density, sodium proves to be the most cost-effective option within its mid-size segment. The data shows that switching from a lithium-ion NMC battery to a sodium-ion battery can reduce the overall cost per kilometer by up to 21.8%. Because sodium cells are so inexpensive to produce, it becomes economically advantageous to install the maximum possible battery capacity. This larger onboard storage allows drivers to rely on low-cost home charging more often, rather than paying the higher rates at public fast-charging stations. For the consumer, this means that for shorter daily trips, a battery that is physically larger and heavier actually becomes the most affordable way to drive. These diverging economics are causing the global electric vehicle market to split into two distinct paths. Lithium and future solid-state batteries will likely focus on the high-performance and luxury markets, where consumers are willing to pay more for long-range capabilities. Sodium-ion is on track to become the standard for the commuter market. With most daily round trips falling between 34 and 100 kilometers, the range limitations of sodium do not impact the way most people actually use their cars. Battery manufacturers are already responding to this shift, building dedicated sodium-ion production facilities specifically to meet this massive commuter demand. Sodium may not provide the longest range, but its abundance makes it the economic key to achieving global climate goals by making electric vehicles affordable for everyone.